Welcome today to this class, and in this we'll be solving a numerical problem related to the dynamics of a first order system. We'll have a look at this problem and solve this problem, and this is a previous year question from GATE. It's a previous year question from GATE. This is from GATE Chemical Engineering paper of 2008 chemical engineering paper, question number 62, which is related to the dynamics of first order. The question is this: a tank of volume 0.25 meter cube and height 1 meter has water flowing in at 0.05 meter cube per minute. The outlet flow rate is governed by the relation. This is the relation F out equal to 0.1 H, where H is the height of the water in the tank and in meter, height of the tank in meter, and F out is the outlet flow in meter cube per minute. The inlet flow rate changes suddenly from its nominal value of 0.05 to 0.15 meter cube per minute and remains there. The time at which the tank will begin to overflow. You have four options, so you have to find out which is the correct option for the time for the tank to overflow after the disturbance. Well, this is related to the dynamics of a tank because the inlet flow rate changes and you're asked to find out the dynamics, the response of the height of the tank. So we need a transfer function relating the height and the inlet flow rate of the tank. The tank can have different types of transfer function depending upon its characteristics of the flow between the flow and head, that is the flow head relationship. So here the flow head relationship is given as this: F out equal to 0.1 H. So this is a flow head relationship. So you find that this is linear, right? This is a linear relationship. This is a linear relationship, and the transfer function of a tank, such a tank with a linear relationship, has been discussed and derived in my earlier lecture titled as PC48. So in this video, in this lecture, the necessary information and the necessary equation of this transfer function has been discussed and derived. Well, the link for this, you might have already gone through this lecture. The link for this lecture is given above as well as below in the description. Okay. Well, so what is the transfer function of a tank which has got a flow head relationship as linear like this, and relating the inlet flow rate and the height. So this is a transfer function, required transfer function Hs by Qs equal to k by tau s plus 1, where k equal to r is a resistance, and time constant tau equal to a into r. A is area of cross section of the tank. As I said, all this information in detail has been described in PC48. Now, so this is a transfer function. You have to evaluate anyway, we have to use this transfer function to find the response H. So this is the response H. We need to find what is H when something is given, when something is troubling in when there is some trouble in QS. Well, we need these parameters R and tau. So R is equal to K. Sorry, the gain is R. And what is the resistance here? So the resistance can be found out from this relation. So if you recall from this lecture, I had used Q naught, the outlet flow rate, equal to H by R. The outlet flow rate I had used there in the lecture Q naught. Here it is given as F out. So that is equal to, that is of the form H by R. So here it is given as 0.1 H. So what is R? R will be, or 1 by R will be 0.1. This 0.1 is 1 by R. So R will be equal to 1 by 0.1, 10. The given units. The units are all consistent. Meter cube, minute, meter cube and minute. So R is 10. And the area of the tank, you are given volume of the tank and height of the tank. So area of the tank is simple, volume by height. Area is volume by height. So this is volume. 0.25 is a volume. So this is a volume and this is a height. So volume by height is area. So area is 0.25 meter square. So area is 0.25 meter square. If you want the units of R, it is minutes per 10 minutes per meter square. Well, so tau equal to A into R. A is 0.25, R is 10. So if you multiply 0.25 into 10, 2.5 minutes. The time constant is 2.5 minutes. Time constant you got as 2.5 minutes. Now we'll go to the problem. What is the problem? What is the disturbance? The inlet flow rate changes suddenly from nominal value of 0.05 to 0.15. So what sort of input is this? The input varies from 0.05 here, 0.05 to 0.15 at 0. So suddenly it varies from 0.05 meter cube to 0.15 meter cube. So sudden jump. So what sort of input is this? So this is a step input. So if you write the step input equation, so this sudden rise from 0.05 to 0.15 represents a step input. So the input is a step input. If you write Q in terms of deviation variable, Q equal to M into UT. What is M? How much is M? The magnitude of the step. The magnitude of the step is this difference. This difference is magnitude of the step. How much it is? So M is 0.15 minus 0.05 equal to 0.1. So M is 0.1 meter cube per minute. So that is step. That is the magnitude of the step. Now we are given a step input. So this input is a step input. And the dynamics is the first order transfer function k by tau s plus 1. So what is the response? What will be the response? So the response is ht equal to mk into 1 minus e power minus t by tau, where k is r, right? K is r. K is gain is r. And this is the standard step response equation. We had also discussed this. If you want to know the reference, we have discussed this in PC37. So you can refer to PC37 where the step response equation has been derived. And m is a magnitude, k is a gain. So I'll substitute gain is here r. So if you substitute m r into 1 minus e power minus t by tau. And this side capital H means what? The deviation variable h minus h's. Well, we need to know what is h's also. Steady state relation given. What is the steady state relation given? So to know the Hs, we go to the steady state relationship. This one, steady state relationship is F out equal to 0.1 H. And before, Hs means initial steady state height. So initially what was the flow rate? Initially what was the flow rate? 0.05, right? Initially 0.05. So points, if you substitute that 0.05 into this equation, you will get Hs. So let me substitute to find Hs. F out equal to 0.1 into H at initial steady state. This is the initial steady state. This is the initial steady state values 0.05. We need the initial Hs, initial steady state. So what will be Hs from this? So if from this, what will we get Hs? So this is going to give me Hs as 0.05 by 0.1. How much it is? How much it is? 0.5 meter. So initial steady state height is 0.5 meter. Now let me substitute all these values in this. In this equation, go to this equation. Let me substitute H equal to, I'll take Hs the other side. Hs I taken, substituted for Hs and taken to the other side. Hs equal to 0.5 plus M is how much? M is 0.1. And R value, how much is R value? M is 0.5, R is 10, right? R is 10. So 0.1 into 10 into 1 minus e power minus t, tau is 2.5. So H equal to 0.5 plus 1 minus e power minus t by 2.5. Now the question is, when will the tank overflow? This is a response equation. This is a dynamics response. This is a dynamic response of the tank. So when will the tank overflow? The tank will overflow when the tank overflow when full height is reached. That is when H equal to height of the tank is 1 meter. So when tank height equal to 1 meter, it is going to overflow. So what is the time at which it will overflow? 1 equal to 0.5 plus 1 minus e power minus t by 2.5. So you solve this equation, solve this for t. What do you get? If you solve this for t, what do you get? Solve for t, you're going to get 1.73 minute. So this is the answer. And do you have an option for 1.73? Yes, you have an option 1.73 here. Option C. Option C is 1.73. So the answer for this question from 2008 paper is option C. Option C is answer. Well, option C is the answer, correct answer. So this problem explains, you get to know how to estimate the dynamics of a first order system. This is the tank first order system with a linear flow head relationship, and the inlet flow rate is changing by a step change, step input. And what is the dynamic response in the height? So that is given by this equation, and from that here we had found This is a dynamic response equation, and from that we have found the time required when will the tank overflow. We can also find out from this dynamic response equation what will be the height of the liquid level in the tank at different instants, at different times. We found out that t equal to 1.73 minute, the tank will overflow. That is, how did you do that? We substituted t equal to, this t equal to we substituted h equal to 1 minute. We substituted h equal to 1 meter. We substituted h equal to 1 meter in this equation. In this we substituted h equal to 1 meter because that is the height of the tank, entire height of the tank, full height of the tank, and solve for t. That will give us the time required for the time at which the tank is going to overflow. Similarly, you can also find, that's a question asked in this question ends with that, the answer ends with that. Now additional information, if you want to know what will be the height of the liquid level in the tank at any particular instant of your choice, that also can be found out from this equation, from this response equation. For example, I want to know what is the height of the tank or height of the liquid level in the tank at 1 minute. I can substitute t equal to 1 minute and find what is the h. Similarly, if I want to find out after 0.5 minute what will be the height of the liquid level in the tank, all you have to do is substitute t equal to 0.5 and find out what will be the height of the liquid level in the tank. So using this response equation, you can estimate the height of the liquid level in the tank at any instant. So in this question, what is asked is simple one question: when will the tank overflow? That is, when h equal to 1 meter, the entire full height of the tank, how long it will take to reach that height. So that answer is 1.73. Hope it is understood. If any comments or doubts, please leave it in the comment section. Please if I like this lecture, please subscribe to this channel and also share it to your friends. We will come across more such problems, more such solutions, more such information in the coming lectures. So don't miss them. See you.